Hello students, and welcome to another video, this time on study unit 3 and logic gates. So what are logic gates? Well, logic gates are logic devices in Next.js, and they carry out logic functions. So they all have inputs and outputs, and their output states are dependent upon the conditions applied to the inputs. Devices that carry out the basic logic functions are often referred to as gates. Guess what do I mean by this? So, I mean that first off, we start with gate definitions. We have a couple of basic gates. Now the first one, we have the NOT or the inverter gate, which looks like this. And what this basically does is, whatever is on the input, whatever binary bits on input, it inverts. So a 1 on this side becomes a 0, and a 0 becomes a 1. So it just inverts the input. Here we have the AND gate. So this is a representation of AND gates in different states. So you can see a 0 and a 1 is a 0, a 1 and a 0 is 0, and it only when both inputs are high, or ones, is the output a high. So this is a and B, and we can write it A dot B, and this means A and B. Now these AND gates can have multiple inputs, but just one output. So now we are looking at the truth table for the AND gates for the inputs A and B. You see we've written the binary here, and 1 is equal to high, 0 is equal to low, and only when both inputs are high, the output would be high. So this is just what we call a timing diagram. So each of these intervals here represent a set amount of time, and it represents the inputs A and B, and then the output, which is X. So like here, A and B, it goes through the AND gate and comes out X. So here we can see at this specific time step, A equals 1 and B equals 1. So the output is also 1. For the next time step, T2, A is 0, B is 1, so the output is 0. For the next time step, A is 1, B is 1, so the answer is output is 1. And then again, for every time step, we draw the output. Now, we might find questions where you have to answer this. We'll give you the timing diagram for the inputs and then ask you to draw the outputs. Now the easiest way is draw the output lines on top and draw down the times or the timings, and then that's easier to draw what the corresponding outputs are. Now we have an OR gate. Now these are all the possible inputs for OR gate. Now OR gate is high if any one of the inputs are high, then the output's high. But if both of them are low, they are low. So this means A or B. A or B. So think of it logically as in logic gates, A or B. So either one of them has to be a high for the output to be a high. Now if you think about the previous AND gates, A and B must be high for the output to be high. And we write it mathematically, A plus B, but in logic, this plus is an OR. Now with, like the AND gate, we can have several inputs, which we write like this. Now here's the OR truth table, and as you can see, if any of the outputs are high, or both of them, then the output is high. So pretty easy. The only condition where you have a 0 at the output is when both A and B are 0. Now looking at the timing diagram for the OR gate, now pay close attention to how the OR gate looks, and every single gate looks differently, and please when you're drawing them, accentuate the differences so we know exactly what you're drawing. Or inside you write OR gate or an AND gate or whatever. So here we have the timing diagram. Now this is actually 2 time sets, but because it doesn't change with them, we just make it 1. And here you can see when either input or both inputs are high, the input output is high. So here only A is high, B is low, but it's still high. Both of them low, low, one of them's high, so it's high, both of them low, and there we go. So here it's low, up here it's high. So now we move on to a NAND gate. So this is basically short for a not AND gate. So it's an AND gate, and the output is inverted. And this is the possible variations for the AND gate with the 2 inputs. And so when both of them are 0, you have a high. If either one of them are, and does a high, it's a high. But if both of them are high, it's a low. So you write it like this, A NAND B, and mathematically we can write it like this. Now here we have the truth table, and as you can see, it's the exact opposite of an AND gate. So with an AND gate, this only condition with a high would be the 1 and the 1, but here the A NAND B is 0, and all other conditions are 1. So A NAND B when both of them are 0 is a 1, and A NAND B when one of them is a 0 are both 1s. Here we have the timing diagram, and please pay attention, this is a NAND gate. So there's an AND gate with a little bubble. So that makes that bubble at the end, makes it a NAND gate. It's the same with the timing diagrams. Both of these for intervals there for X is low. So just go through the timing and then compare. Here you have a high and a high. High and high means a low for an AND gate. Here we have a low and a high, which means a high for a NAND gate. Here we have a NOR gate, and this is basically a not OR gate. So here we have all the possible permutations of a NOR gate, a 2-input NOR gate, and it's basically the inverse of an OR gate. So the only output where you have a high is when both of them are low. So you write A NOR B, and this is mathematically how you write a NOR gate. So this is the truth table for NOR. So here you can see A NOR B when both of them are 0s or lows is a 1. The rest, whenever you find a 1, is a low. Okay, so this is the truth table for NOR gate. A NOR B when one of them are 1s are both 0s output, and A NOR B when both of them are high is a low. And here we have the timing diagram for a example timing diagram for a NOR gate. You see you have a high and you have a low, so that means a low. Here both you have A and B are lows or 0s, and that is a high. So it's only high when both A and B are 0s or lows. Now we come to an exclusive OR gate, or XOR gate, and these are the permutations of an exclusive OR gate. So when both inputs are the same, either both 0s or both 1s, it's a low, and when they are different, a 1 or a 0 or 1 or 1 or 0, then it's high. So this is the truth table for an exclusive OR gate. As you can see, both A R and B, or A or B, exclusive OR B, is 0, and here you have they are different, 0 and a 1, 1 and a 0, and they're both 1s, and 1 and a 1 is a 0, so that's an exclusive OR gate. And here we have a timing diagram for the exclusive OR gate, which looks like this. Remember this? And so you have a 1 and a 1, both are highs, they're the same, so that's a low. You have a 0 and a 1, both are they're different, so that means a high. You have a 0 and a 0, they're the same, so that's a low for the exclusive OR gate. And now we have the exclusive NOR gate, which is the inverse of the exclusive OR gate. So here it's exact opposite. It's only high when both inputs are the same, and it's a low when they are different. A 0 1 or 1 0. 1 1 it's high, 0 0 it's also high. Here we have the truth table. As you can see here, both of them are, we have when A is 0 and B is 0, then you have a 1, a high output. So when A is 0, B is 1, you have a low output. And then it goes on until A is 1 and B is 1, and that gives a high output for the exclusive NOR gate. So now we come to integrated circuits. Now integrated circuits are just little circuits or chips, if you want to call them that we use that contain all these gates and all these logic gates inside them. Now they basically come in this form. They can have more pins. The specific ones we're mostly working with has 14 pins. Now if you look at your chip, at either one of it there's going to be a dot or a little wedge cut out. That means from that wedge, the first one on the left side is 1, and then you start counting 1 2 3 4 5 6 7 8 9 10 11 12 13 14. So always when the side of the wedge or the dot, the first one on the left side is always 1. Now you will have they also come in through hole, where with pins where you stick them through the hole, or surface mount, where they are mounted to a surface. This is a diagram they would get with in the data sheet. Data sheet is something that explains the logic gate and how it works and maximum voltages and all kind of stuff. And they have diagrams like this. So inside pin 1, the one on the left side of this little wedge, is one of the outputs, the A output of a NAND gate, and B is the other input of the NAND gate, and then 3 is the output. So here we have a 4 or a quad input NAND gate IC. Here we have to connect it to ground, and pin 14 we have to connect it to positive voltage. Depending on what type of chips you use, but we're using TTL, so it will always be in TTL 5 volts. Otherwise, if you don't connect it to 5 volts here and ground there, your chip will not work. So here we have the notation. Most of all the chips, you will look at it at the top and there will be writing on it, and this denotes what chip you are working with. So usually the first 2 letters is the manufacturer. There is 74, it's the series number, 74 series TTL. Then you have the logic family, advanced low power Schottky. Don't worry too about it. The logic function is the next couple of bits. In this case, quad input NAND gate. And then you have in, which is the packet type, which is but usually if you have your chip, you look at it and then you Google the letters in this order that you find on it, and you will come to the correct data sheet for it. So we use a data sheet, and it tells us how to wire up our ICs and how they work and what voltages we must apply to them, and also how they are internally structured in terms of where the gates inputs and outputs are. So yeah, this was just a video about study unit 3. Now deals with just an introduction to the logic gates, and throughout this course the logic gates will be more and more important to what we do. So it's very important to understand the basic logic gates, understand what a NOT gate is and the truth table for it. What is an OR gate, an AND gate, exclusive NOR gate, a NAND gate. All these gates you have to study, and you have to know the truth tables off by heart. So that when you're in a test and we ask you what an OR gate is, you can explain and then also know exactly what an OR gate does when it has a certain amount of inputs. So it's very important to have a very firm grip of what this chapter is and all the logic gates. Okay, good luck.